Hello everyone, Mr. Fawcett here, and today we have a lesson on deductive reasoning. So a couple videos back we talked about inductive reasoning, which is where someone takes specific examples and tries to make a general conjecture. So one of the examples we looked at was if somebody visits a few colleges and all of those colleges have on-campus housing for students, well, that person then using inductive reasoning could say that all colleges have on-campus housing. So they're using the few examples or the few colleges that they've traveled to make a general conjecture about all colleges. Now, it doesn't mean their conjecture is true, but that's just an example of what inductive reasoning is. It's using specific examples to come up with a conjecture. Deductive reasoning is a little different, and we'll get there shortly. But before we do, let's look at a few review problems. So for numbers 1 and 2, you just need to underline the hypothesis of the statement. For number 3, you need to determine whether the conditional statement is true. If it's false, then you need to give a counterexample. So pause the video, take some time to do that, and then I'll see you back here. Okay, so if we remember, the hypothesis is going to follow the word if. So in our first statement, if a mapping is a reflection, then it is a type of transformation. So our hypothesis is if a mapping is a reflection. Our conclusion follows the word then. So our conclusion is it is a type of transformation. Now, if we look at number 2, sometimes they don't give us the words if and then. So we have to determine what's coming first and what's then reliant on the other. So our statement is the quotient of two negative numbers is positive. Well, which of those is reliant on the other? Which of those must come first before the other one can occur? Well, we need to have the quotient before we can determine whether it's positive, negative, or zero. So the quotient of two negative numbers is our hypothesis. Is positive would be our conclusion. All right, for number 3, it says determine if the following conditional statement is true. If it is false, then give a counterexample. So our statement is if x is a real number, then the absolute value of x is greater than 0. So if we remember to the only time a conditional statement is false, right, that occurs if our hypothesis could be true and our conclusion false. So if we can find an example where the hypothesis is true and the conclusion's false, then we can say that the entire statement's false. Okay, so can we find a real number where the absolute value of that number is not greater than 0? Well, maybe you figured it out, but our counterexample would be when x equals 0, right? Because the absolute value of 0 is equal to 0, but 0 is not greater than 0. So this is false. And our entire statement, the conditional statement, is false. Okay, let's get into our little introduction. So you all are going to read scenarios 1 and 2, and then you're going to answer the question down below. So go ahead, do that. Take a few minutes, and then we'll have a discussion. Okay, so scenario 1 is talking about how sinks and toilets drain based on whether you're in the northern or southern hemisphere. So the conjecture here is that they swirl in opposite directions based on whether you're in the northern hemisphere or the southern hemisphere. However, if you were to actually observe the draining of a sink or toilet in each hemisphere, you would see that they drain in the same direction. Scenario number 2. There's an idea that eelskin wallets will destroy the magnetic chip on the back of a debit or credit card because an electric eel skin holds an electric charge. So that electric charge maybe messes with the magnet. However, this is a myth because eelskin wallets are not made from electric eel's skin. So our question is, what was the difference in how each idea was disproved in the above scenarios? Is there a way to change how you would disprove the second idea to match the style in which the first idea was disproved. So in scenario 1, the way we disproved the conjecture, right? The conjecture was that the sinks and drains, or the sinks and toilets, drain in opposite directions. The way we disproved that was actually going and observing. So if you actually went to the northern or the southern hemisphere, you could see that they actually drain in the same direction. So it was based on an observation. In scenario number 2, we just used facts, right? The conjecture was that eelskin wallets will destroy the magnetic strip on the back of a credit or debit card because an electric eelskin holds an electric charge. Now, we're disproving this simply by noticing a discrepancy in the facts of the story. So, eelskin wallets are not made from electric eel skin. So therefore, our conjecture doesn't make sense, right? If they're not made from electric eel skin, then there's not going to be an electric charge from the skin in the wallet because the wallets aren't made from the eel skin. So the question is, how could we change the way we disprove the conjecture in the second scenario to match the way we disproved it in the first? Well, we could do an observation, or we could do an experiment, right? We could buy an electric eelskin wallet, we could put a credit card in there, and then we could try to use the credit card later and see if the magnetic chip was destroyed. That would be data that we've collected based on an experiment, rather than just saying, well, the wallets aren't made from electric eel skin, so therefore there can't possibly be that charge that they're talking about. Both ways are valid, right? We can do an experiment and gain data on whether or not the chip was destroyed, or we could look at the fallacy in the original argument, right? The original conjecture was assuming that the wallets are actually made from eel skin, right? But maybe they're just called eel skin wallets because they look like eel skin, right? But they're not actually made from eel skin. I don't know what these wallets are actually made of, but based on what they're saying here, if the wallets aren't made from eel skin, then we wouldn't have to worry about that electric charge to begin with. Okay, I'll put this down into words so that we have something on paper. All right, so I just wrote down what we had been discussing. The first scenario used an observation, while the second used facts about eelskin wallets. If we wanted to treat the second scenario or approach the second scenario the same way the first was approached, well, we could have tested a wallet with a credit card to see if the chip got destroyed, rather than relying on knowledge about the wallets themselves. Okay, let's get into some vocab and talk about what deductive reasoning is. So, just a quick review on inductive reasoning. Inductive reasoning is a process of reasoning that a rule or statement is true because specific cases or specific examples are true. In our example, Justin concludes that a ball thrown in the air will always come down to the ground because that's what happened when he tested his hypothesis, right? So if you throw a ball up in the air and it always comes down, well, you could make a conjecture that it's always going to come down based on the examples that you've encountered, right? Or the observations that you've had. Deductive reasoning, right? A little bit different. Deductive reasoning is the process of making conclusions based on general premises that are assumed to be true. General premises that are assumed to be true. You can think of this as making your conclusions based on facts that you know. This doesn't require you to have to do any experiments or for you to have to observe anything yourself. You can base your conjecture on what you already know, so prior knowledge. So the same type of example, right? But we have Megan now instead of Justin. And she also concludes that a ball thrown in the air will always come down to the ground. But she does this because she understands that the force of gravity is acting upon it. So rather than test the ball herself, she just uses the idea of gravity, knowing how gravity interacts with objects, to make the conjecture that the ball will always fall back to the ground. Okay, let's look at two laws here. The first is the law of detachment. So we're back to our P implies Q statements. So if P implies Q is true and P is true, then Q must be true as well. So this just goes back to our understanding of conditional statements, right? The only time a conditional statement is false is if the hypothesis is true and the conclusion's false. So if we know that the statement's true, right, this time we're being told that P implies true, implies Q is true. Well, if the hypothesis is true, then Q, or our conclusion, must be true as well. Because if Q wasn't true, then the statement right here would be false. But we're told at the beginning that it's true. So let's see this law in action. If you get an A in this class, so we're over here now. If you get an A in this class, then you will pass for the year. Okay? So Dan got an A in the class. Well, if our statement was true, right, if this conditional statement was true and the hypothesis turns out to be true, well, then our conclusion must be true. So Dan passed for the year. Again, this is called the law of detachment. The law of syllogism, a little bit different. So it says if P implies Q is true and Q implies R is true, then we can also conclude that P implies R. So let's look at an example. If Mark scores a goal in his game, then his dad will take him to get ice cream. Okay, so we have a P, and let me write show what our P's and Q's are. So that is our P, right? Our Q is then his dad will get him ice cream. And then we have this other conditional. It says if his dad gets him ice cream, which is, again, a Q, then Mark will be too full for dinner, which is not a P or Q, so we're going to call that R. So this Q is a conclusion of one statement and a hypothesis of the other, so it links the two statements. So based on the law of syllogism, if P implies Q is true and Q implies R, then P implies R. That's also going to be a true statement. So based on our scenario, if Mark scores a goal in his game, then his dad will get him ice cream. And if his dad gets him ice cream, then Mark will be too full for dinner. Well, we can say that if Mark scores a goal, then he will be too full for dinner. And again, that's because this Q is linking both of these statements together. So we can essentially cut it out to make another true statement. All right, we're getting close to 15 minutes, so let's see if we have some practice. And we are just going to make this one video. It may go a little over 20 minutes, but I think that's going to be better than breaking it up into two. So here's our practice. It says, write the conclusion that can be made from the given information. If there is none, then state it as so. Also write which law you used for each problem. You can abbreviate the law of detachment as LD and the law of syllogism as LS. So take some time to work through these. You have 1, 2, 3, we'll just do 1, 2, and 3 for now. And then we will come back and review. So we are told that the conditional statement we're told is that if two angles sum to 180, then they are supplementary. So let's first determine whether this is true. If two angles sum to 180, then yes, they will be supplementary. So there's never a case where two angles sum to 180 and they're not supplementary. So our conditional statement is true. Then we are told that we have two angles, angle 1 and angle 2, and those measurements sum to, those measurements are 60 and 120, which means they sum to 180. So what conclusion could we make here? Well, we could then say that angle 1 and angle 2 are supplementary. And this would be based on the law of detachment. So the law of detachment says if our initial conditional statement is true and the hypothesis is true, then the conclusion has to be true. Okay, number 2 says if you get 3 tardies in a week, then you will serve a detention. So that is our conditional statement. We are then told that Jessica is in detention. So what conclusion can we make? Well, turns out we actually can't make a conclusion here, right? This may look like a law of detachment problem because we're given a conditional statement, that's true, and then we're given a piece of information, but the problem is this piece of information is not the hypothesis. This is the conclusion. Just because the conclusion is true does not mean that the hypothesis has to be true. And you could think about this, right? There could be other reasons why Jessica is in detention. We can't determine that Jessica got 3 tardies because she's in detention. She could have got detention for being disrespectful or any one of the other number of reasons you may need to serve a detention. If we had been told she had gotten 3 tardies, then we would be able to say she will serve a detention because having 3 tardies ensures that you get a detention. But being in detention doesn't necessarily mean you're there for getting 3 tardies. So no conclusion, which means we are not going to have a law to use either. Okay, let's look at number 3. It says, if an angle measures less than 90 degrees, then it is an acute angle. If an angle is acute, then it is not a right angle. And then it gives us a piece of information. So whenever you see 2 conditional statements, you want to be checking to see if we can use the law of syllogism, right? Because that's P implies Q and Q implies R, then P implies R. We have to make sure that these statements are true, though, before we just say that P implies R. So let's look at the first one. Is this statement right here true? So if an angle measures less than 90 degrees, then it is an acute angle. That is true, right? The second statement, if an angle is acute, then it is not a right angle. Well, a right angle is a 90-degree measurement, and that can't be true if the angle is acute, because an acute angle has to be less than 90. So this second statement is also true. So for the first statement, we have P implies Q. Let's make a little better Q. For the second statement, we have Q implies R. And then we are given a piece of information. It says measurement of angle C equals 68 degrees. This is really a P, right? Because P is if an angle measures less than 90 degrees. So if we have a P, then we can imply an R. So our R is, then it is not a right angle. That's our R, that's our conclusion. Angle C is not a right angle. And we would be using the law of syllogism here. The last problem we're going to look at, we're actually going to skip down to number 5. So here, directions say determine whether the given conclusion for each problem is valid based on the given information. If it's not, explain why. So number 5, it says if a number is evenly divisible by 4, then it is evenly divisible by 2. The second statement is if a number is evenly divisible by 2, then it is a whole number. So the conclusion here is if a number is evenly divisible by 4, then it is a whole number. So they're using the law of syllogism, right? They have two conditional statements. And then they write this would be a P implies R, right? So here's our P implies R. Up here was our P implies Q. And then we had a Q implies R. So if P implies Q and Q implies R, well, then we can say that P implies R. So think back to what must be true for us to be able to use the law of syllogism, and then write down a conclusion saying whether or not this conclusion up here is valid. Okay, so for the law of syllogism, we have to have two conditional statements, and they have to be linked by a common Q, right? And they are. So the Q here is a number being evenly divisible by 2. What also has to be true, though, is that the conditional statements have to both be true to start with. Okay, so we have to check to see that this green one is true and that this red one is also true. So let's check the green. If a number is evenly divisible by 4, then it is evenly divisible by 2. This ends up being true. Okay, there's no number that is divisible by 4, but not divisible by 2. And you could test some examples to try to confirm our conjecture here. So the green is true. Let's look at the red. Let's do that in green, though. So green is true. The red says if a number is evenly divisible by 2, then it is a whole number. So whole numbers being 0, 1, 2, 3, 4, 5, 6, etc. Well, for this to be true, we would not be able to have a number that's divisible by 2, but not a whole number. So are there any numbers that are divisible by 2 that aren't whole numbers? Well, any negative number that's divisible by 2, right? Negative 14, that's divisible by 2, but it's not a whole number because it's negative. So because this red statement is false, we cannot make a conclusion using the law of syllogism. And you can see that this conclusion would be false, right? If a number is evenly divisible by 4, then it is also a whole number. Well, no, right? There are negative numbers that are divisible by 4 evenly, but they're not whole numbers. So no, not valid, because second conditional statement wasn't true. So we're going to cut the video off here. We're pushing 25 minutes. You can go back and look at number 4, jump ahead to number 6. Number 6, you get to create your own statements and try to work in the law of syllogism. We do have one more lesson in this unit. It's on what a biconditional statement is. So enjoy the rest of your day, and I look forward to seeing you for the last video in this unit.